All right, peoples. Electrolytic
Electrolytic.
electrolytic cells. So what's an electrolytic cell? It's a non-spontaneous electrochemical cell that we drive with a battery. So all the electrochemical cells that don't work, we say, oh, they're not spontaneous. Throw a battery on it and we drive it and we make it work. That's pretty much what it is. All right? So basically, a chemist would say we use an external DC. What's DC stand for? Direct current power source is used to force a non-spontaneous reaction to occur. So, electrochemical cell, which is what we did in part one, the electrons flow from anode to cathode. And that's controlled by the redox chemistry. Whichever one was the stronger oxidizing agent would force the electrons to move in a certain direction. An electrolytic cell, we still say it flows from anode to cathode, but everything is controlled by the battery. Okay? So if we look on the left here, we got an electrochemical cell. We have a zinc anode with zinc ions. We got a copper cathode with copper. At the cathode, because the electrons are flowing this direction, the copper 2 plus is picking up the electrons to form copper solid. And the zinc is oxidizing to provide that. And we have E naught of the copper is 0.34 volts, and the zinc is 0.76. So we get an overall reaction where copper 2 plus zinc becomes copper solid and zinc plus 2 with an E naught or reduction potential of 1.10 volts. Okay. We say the anode is negative because that's where the electrons are produced and then they move away from it. And this is all spontaneous. That's an electrochemical cell. In an electrolytic cell, we reverse it by sticking a battery on it. So that means the electrons are flowing in this direction and are going towards the zinc. So the cathode has been flipped. The cathode is the zinc ions picking up two electrons to form zinc solid. And at the anode, because the anode is electrons are flowing away from it, the copper is being oxidized to copper 2 plus. So the overall reaction is the reverse of the previous one. So it's zinc plus 2 plus copper solid, zinc solid plus copper 2 plus, aqueous. How strong does the battery have to be? What's the minimum strength, do you think? So the spontaneous reaction is 1.1 volts pushing this way. So if you want it to go the other way, the battery's got to be stronger than 1.1 volts. If it's less, then that wins. Okay? All right. Flip the page, please. So, we've already defined it. Do we want, I guess we'll define it again. Force a non-spontaneous reaction. So there's three types of electrolytic cells, which we call electrolysis. There is type 1, which is molten salts. With inert electrodes. What are inert electrodes? What does inert mean? They don't react, all right? And when I say molten, that means there's no water. Basically, it's a melted, well, sodium chloride if you want to use actual salt. You melt the sodium chloride, okay? But molten means there is no water in this reaction. Type 2 is the electrolysis of aqueous solutions. With inert electrodes. And then the final type, type 3, is electrolysis of aqueous solutions with reacting electrodes. This is where we do our electroplating. Okay. And just a quick review, the inert electrodes play no part in the chemistry. All right, so you don't need to have two separate beakers like we did in electrochemical cells. All right, you can do it all in one beaker. So we look at this, the electrolysis of molten NaCl. These are the simplest in terms of the chemistry. They're one of the hardest to do in practicality because it's molten NaCl, which means it's melted, it's liquid. All right, so it has to be at 800 degrees Celsius. So we won't be doing this in class, all right? I know. Yeah, we'll get to like 790. So the chemistry is very simple, but in practicality, doing this stuff is actually quite difficult, all right? So the cathode. We throw a battery on here. The electrons are flowing in this direction. They build up on the cathode. As they do that, it's molten NaCl in here, right? So the sodium ions pick up the electron. Remember, the cathode is where reduction occurs. Sodium picks up an electron, it becomes liquid sodium, because we're at 800 degrees. So it's liquid sodium, right? E naught of that is negative 2.71 volts. At the anode, so electrons are moving away, so this becomes a positively charged electrode. The chlorine, which is negatively charged, is attracted to that anode, or to the anode, and you get 2Cl minus in liquid form goes to Cl2 gas plus 2 electrons, which isn't a great thing to have happen unless you're in a very controlled. The E naught of that is negative 1.36. And I'm getting these numbers from your data package. So if we look at the data booklet, if we look, sodium, there's sodium right at the bottom here. It's being reduced at the cathode, and chlorine, which is up here. So we're flipping the reaction, right? We're flipping the chlorine to write 2Cl goes to Cl2 gas plus 2 electrons, and when you flip it, it becomes negative. That's why the overall reaction here is sodium plus 2Cl minus sodium liquid plus Cl2 gas, which has an E naught. Add those together and you get negative 4.07. So we know it's not spontaneous, but we're putting a battery on it. How strong does the battery have to be? Above 4.07 volts. Okay? And this is also a dangerous reaction because when liquid sodium hits chlorine gas, you get a massive explosion. So not only are you going to be doing it at 800 degrees Celsius, you got to find a way to keep those things apart, if possible, so that you don't have a big boom of molten and liquid sodium flying all over the place. That wouldn't be good for people. And so this bit is the overall reaction. In order to force the chemistry, the external battery must always exceed the voltage of the internal cell, i.e. what the electrochemical cell would need to run spontaneously. Okay? That's type 1. I'm going to stop the video here, give them some time to do some questions, and then we will pick it up in 10 minutes, people. See you then. See? Now they're all